No.
All right, fine. Thanks for that lovely intro, Emily. So, thank you, Don et al. For the opportunity to talk about my least favorite topic, and that's atmospheric retrievals, aka curve fitting for planets. What is a retrieval? There is some maths behind it that I will go through, but I think of it as a collection of tools or philosophies that we need to use or leverage to link the observations to what we want to learn about the atmosphere. So I want to take you on that journey, and I want to just advertise our group at ASU. The Dexter's Lab stands for Dwarf Exoplanet Exploration and Remote Sensing. It's a backronym, and if you don't fall asleep, you'll see a cute picture of the Dexter Corgi that it's named after at the end. So we saw a lot of motivation earlier this week, some nice talks from Heather, Hannah, Laura, and then from Mark and Lee and Laura this morning about the things we want to learn about planetary atmosphere. So I'm simple-minded, so I like to break it down into things I can understand, into some simple questions like, how do atmospheres form and evolve? Does atmospheric composition reflect the formation conditions? What are the range of planetary climates? What are the processes that are driving the chemistry in the atmospheres? And of course, what is the prevalence of biosignatures? And do terrestrial planets, for instance, have atmospheres? And so I think of these as breaking down the study of planetary atmospheres or exoplanetary atmospheres in particular into origins and processes. So here's our classic, mostly wrong picture of how a planet forms through our core accretion. And there's a lot of magical things that now happen here with pebbles and drifts and vortices and stuff like that. But at the end, you end up with a core of sorts, a rocky core that then accretes gas. And so under this mechanism of core accretion, which is what we think many of the planets that we're observing in transit, how they form, there are telltale signs of that formation pathway. So one of these examples is this mass metallicity relationship that you heard about earlier, where we think that lower mass planets, because they tend to have a relatively thin atmosphere compared to, say, higher mass planets, are going to be more sensitive to infalling planetesimals at the late stages of planet formation. So we might expect objects like Uranus and Neptune-sized planets to be enriched in metals. We also might expect this classic picture here, where depending on where the planet forms in the disk and when it migrates, whether or not it migrates before or after the gas and dust dissipate, is going to influence the elemental ratios, for example, the carbon to oxygen ratio or the nitrogen to oxygen ratio. So these are the examples of the kinds of things we're trying to measure, the metallicity of the atmosphere and the elemental abundance ratios, so that we can connect this back to the formation conditions. And if we can do this at population level, measuring hundreds, thousands of planets, as Mark had talked about earlier today, then we can start making headway. So how, we have to be able to take the observables and convert those into elemental abundances. And these are some examples of the processes. And Julie did a nice job the other day talking about the chemistry of planetary atmospheres, but there's all sorts of processes happening in exoplanet atmospheres, like the radiative energy balance. There's 3Dness happening that we're going to hear more about from Emily tomorrow. Don't know why that popped up. How does the chemistry change with temperature? What role does photochemistry and vertical mixing and horizontal mixing play? And how do those change with gravity, temperature, mass, all of that stuff? So there's a lot of processes that we're trying to learn about, and we have to understand these processes to be able to correct or account for them when we're trying to infer things like the elemental abundances, so we can address the formation question. So everything's tightly coupled in a way. So I like what are called Jacobians. So in life, you can just linearize everything. My last name is Line, so by definition, that's what I do. So I think of the whole problem of trying to back out information from a spectrum and into what we're learning about the atmosphere. It's just a simple matrix inversion. It's trivial. We can all just go home, right? So the physics that you're trying to learn is some vector of things like composition, temperature profile, whatever. And then you have the observables, say a spectrum, and then you have this mapping, this matrix A, that describes how your observations respond to a changing in physics. So sort of a sensitivity grid, if you will. So there are things that we want with observations we can get. So these are what we know about, except there's often debate as to what we want. This is what TACs talk about. There are nuisance physicses, and we can debate what we think nuisances are. Clouds can be a nuisance, or clouds can be a thing we want. Stellar contamination can be a nuisance, or it can be a thing we want. We have things we want to know, but we can't yet observe them. I was talking about reflected light off of terrestrial planets. These are things we want, but we don't have the technology to do it. And I think perhaps more scary are the things we don't know we want with the observations we don't know we need, because all of this stuff is coupled. So there's this is a sparse matrix, right? There's a lot of zeros. So Hannah and Laura and Paul gave a very nice overview of the physics that go into producing a transmission and an emission spectrum. Probably shouldn't be showing half of these, but whatever. So this is an example of a transmission spectrum from JWST. You see all the nice bumps and wiggles. And as we saw from Hannah, a transmission spectra, these wiggle sizes depend on the scale height of the atmosphere, which depends on temperature, gravity, and the molecular weight. So you change those, you can change the amplitudes of these features. But it also depends on the combination of the absorption cross-section, so the wiggliness of the individual molecules and atoms, and also their relative abundances. So transmission spectra contain information along the limbs of the planet about the opacity sources and about the bulk composition of the atmosphere. And then on the flip side, in emission, as we observed during secondary eclipse, or if you're observing directly imaged planets, or if you're observing isolated brown dwarfs, emission spectra are sensitive to things like the temperature gradient in the atmosphere and also the abundances. So based off the physics and the geometry of which we are observing these planets, we can expect that these are the pieces of information that we're going to be able to pull out of these kinds of data. And as Lee had mentioned earlier today, there's degeneracies. And what are degeneracies? That means that there's correlations amongst a parameter. For instance, in the scale height, I can increase the temperature, but also increase the molecular weight of the atmosphere, and I can still maintain the feature size. Or if I have overlapping gases at a same wavelength, I can increase the abundance of the other and decrease the abundance of another one and still get the same feature. So that plays a role into how well we can constrain certain properties of the atmosphere. So here's cuts off the citations, a nice figure by Ryan McDonald illustrating the flow chart of the components that are needed in what I'll just call the retrieval philosophy, right? So you need some kind of Bayesian estimator, and those of you who did the light curve fitting routine yesterday with Eureka, you have some experience with this, or some sort of sampler that allows you to penalize a model comparison to a data. But you need a model, right? And so how do you parameterize that model? What are the types of pieces of information do we need to put in that model? And I sort of explained that on the previous slide. And you kind of iteratively go through this process to get a quote unquote answer. But there's uncertainties in all of these things. And that's what makes doing retrievals or the retrieval philosophy difficult, rather than, because you can go PIP or PIP or whatever it is, install any old code that does a thing, but you really need to understand what all those things are doing. What are all these sources of inputs, and how does changing these inputs, as Lee mentioned, affect your result? So this is the time for you to take your nap. So this is where the math happens, but I have to go through it. And if anyone, if you're a grad student or an undergrad or a postdoc or whatever, this is, I think, a great book that walks you through the whole frequentist statistical philosophy through the Bayesian statistical philosophy. I know Jorge and Mara, I think you guys took my astrostats class, so you guys can come down if you want. So what is the basic idea, right? So what are the data? An individual data point, a datum, is really a reflection of a probability distribution of that point being somewhere, right? And so we want to come up with a model of our atmosphere to explain a spectrum, let's say, that maximizes the probability of going through all of these data points. And so these are all those kind of components that we're going to have to worry about. So we have to go back to good old Bayes' theorem, which is effectively saying that the probability of a given hypothesis being true, given the data, is equal to our prior probability, so our often incorrect knowledge of how we think the universe works before we make a measurement, times what's called a likelihood, which is the probability that it would have gotten that data given this hypothesis. And then this guy right here that everyone just throws away, but this is important, this normalizing factor is basically the probability of your data over all of the models. We'll come back to that in a minute. So there are two problems that we're trying to solve. There's no way I'm going to get through all this. There's two problems that we're trying to solve when we do, I'll call it Bayesian inference, retrievals, whatever. There's the model selection problem. So what is the simplest model that can adequately explain my data, right? Should I fit this thing with 90 parameters or should I fit it with one? How do I choose between them? And then under a given model or with a given model, what are the range of parameters in that model that can explain my data? And this is often where our inferences about the planetary atmospheres come from, like the carbon to oxygen ratio and the metallicity. But these two interplay off of each other because you can, pit models against each other, and how do you choose which models are the ones we should be using? So parameter estimation, basically, instead of having an individual hypothesis for say like the universe is expanding or not expanding, let's say we have a single parameter theta, there's infinite hypotheses for what that parameter value could be within some prior range. So we might say that this constant could vary between 0 and 10. And so we would say this is the allowed range for which we think that parameter could fit. And then say we could compare that parameter to some data. Say you have some scatter plot of just a flat line. You can say compare what is the probability that I would have gotten a data point given that flat line value or that model, given the error bars, and you can compute that using a Gaussian likelihood function. You guys have heard of chi-squared before. Sorry, I didn't write it down, but you basically compare the data minus the model relative to the error bars. And that'll give you a sense for whether or not your model is doing a good job. And I sort of explained this already. And then if you have, you can integrate over all of your model space to get this global likelihood, which is what you ultimately use to do the model comparison. And then if you have a model that has multiple parameters, let's say theta is your C to O ratio that you care about, and phi is like cloud, and you're like, I don't care about the cloud, I want my C to O ratio. You can integrate out over this thingy you don't want. That's called marginalization. And then that basically folds in the fact that maybe this is degenerate with this, and it effectively propagates the uncertainty on this thingy into this thingy at the end. And I'll show you an example of that. Blah, blah, blah. I'll skip this, but you can use this marginal likelihood, the integration over your likelihood times your prior space. So basically, this is penalizing more complex models over simpler models, but a more complex model with more knobs can often fit your data a little bit better. So how do you strike that balance? That balance is dictated with this, what's called a Bayes factor that is used very heavily in our field. And I'll show you some examples and scary things from that in not too long. So you can do model comparison with this. And so there are different ways. How do you do this? I showed you Bayes equation, but like you want to do this for reals. You kind of, I think, did this yesterday. You guys used Dynasty, I think, was it? I didn't do yesterday. And so that's a flavor of Markov chain Monte Carlo and nested sampling. I kind of lumped those two together in my head. That's wrong. There's optimal estimation, which Lee talked about a little bit, but effectively these are like gradient-based search algorithms that basically compute the derivatives of the parameters of the observables with respect to the different physics or parameters you want to find a local minimum and then do a point estimate of the uncertainties, assuming Gaussian shaped posterior. And then of course there's a good old-fashioned grid search where you just brute force a grid of models and then you compare each model to your data and ask, is my chi-squared big or small? And you can make a map. And at the end of the day, you end up with these ugly things that are called corner plots or stair pairs or pair plots or whatever. These are the answer in a way. And this shows the correlations amongst the different parameters, and you can plot different, like your 99 percentile or your 68 percentile. What is the probability? What is the probability distribution of your model given the data? Effectively, what this is. All right. So here's the first sort of application of retrieval in the exoplanet literature on this lovely back in the day data set from Spitzer of HD 209458b. Sorry, chuckle a little bit. It's cool. where they did a grid search. They basically had like a 6-parameter temperature pressure profile that could give you different shapes and wiggles in the atmosphere. And then they played around with the water abundance, CO abundance, CO2, other things, and they could make these maps, these chi-squared distribution maps. And then shortly thereafter, a couple of us, like Lee Fletcher and myself and some other folks at the time, borrowed the methods from the solar system way of doing retrievals, this optimal estimation method, which is effectively chi-square minimization with a prior term. Sometimes we call that a cost function that you try and minimize, but effectively this falls out of Bayes' theorem, where this is basically chi-squared right here. Instead of having like 1 over your error bars, this is a matrix where the diagonals are 1 over your error bars squared. And then oftentimes what we do when we use this type of method is we linearize our forward model, like I talked about before, where we say, instead of having some complex radiative transfer model where, I put in composition and temperature profile and all this other stuff, I just assume that that's going to be some matrix of gradients, this K, times some change in those parameters. I didn't explicitly write that out, but if you solve, if you take the derivative of this and set it equal to 0, you can back out what your final state should be as a function of these different parameters. This SA right here is a matrix that contains what you think your prior uncertainties on each of these parameters are, your X, your state vector. And you can iteratively solve this, and you get these nice diagnostic tools like your posterior error matrix. So this basically describes the uncertainties on each of your parameters after you do a fit. And this is an example of what this Jacobian would look like, the D observable D parameter in your model. Like, how does changing the water abundance by some fraction change the shape of my spectrum? So you use that information combined with the data to basically retrieve spectrum. So here's an example video of this happening, where you start out with some crappy initial guess for what you think the temperature is, and you iteratively go through and you relax to the true state, and you can watch how the abundances sort of approach the true answer. And you're like, well, it's not, you're getting the wrong answer. And it's like, well, it's because it's falling into a local minimum, or could be the random noise instance, for instance. Just to go back here, the advantages of this is a fast way of doing things, and you have this powerful diagnostic matrix formalism that the machine learning community kind of reinvented. And then this has been extensively tested in Earth and solar system sciences, so it's got some heritage, but it does assume that your priors and your posteriors are going to be Gaussian distributed, and you can get stuck in local minima. So it's good when you have like high signal to noise broad wavelength coverage data. Here's an example of the more commonly used methods, the Markov chain Monte Carlo. This is an example using MC on a brown dwarf, where you can twiddle the temperature at each altitude of the atmosphere, and you can see how it relaxes as it's fitting the spectrum. MCMCs, or similarly nested samplers, are nice because you can have any arbitrary likelihood function. It doesn't necessarily have to be a chi-squared. You can have an arbitrarily shaped prior that you put into these, and so you really do get a full exploration of the parameter space. And you can do fun things like hierarchical Bayesian modeling, where you have stuff like hyperparameters and things like that are over my head. The primary con is that you do have to evaluate millions of models, hundreds of thousands and millions of models, so they take a minute. But there's a lot of work that's going into ways of speeding that up. And at the end of the day, you're left with a corner plot, a posterior probability distribution, and these individual histograms are what would be the marginalized probability distributions for each parameter. So it's basically integrating out, say, over all of these other guys right here. What is my methane abundance, right? This is how you would describe that there. Okay, so that's sort of the formalism, the basic idea. There's these tools. There are 972,000 different MCMC packages you can download on the internet. Exactly that number, no. All effectively do the same thing. Some are faster than others in certain situations. But I think a lot of the, philosophy of doing retrieving, is in how you parameterize the atmosphere. So as soon as you make a choice of a model, you've already pigeonholed yourself, all right? You've already made an assumption. Like, I'm going to use a model and I'm going to fit for these 6 gases. You've already limited your range of what you're going to find. You're going to find something about those 6 gases, right? So let's talk about what some of those assumptions are. And I just wanted to highlight this again is how do you populate this, right, philosophically? So here's a nice grid that Vivian Parmentier and I kind of put together probably after a lot of beers. I was thinking about the different choices that we can make when constructing a forward model. So we have a choice in how we can choose a temperature profile. Do we have a wiggly temperature profile? Do we have an inflexible temperature profile? We have a choice in how we parameterize the chemistry. Do we not assume that chemical species interact with each other and that you can get chemically aphysical solutions? Or do we impose some sort of chemistry to ensure that we comply with physical reality? What do we do with clouds? I don't even want to touch that. The geometry, we're looking at disk integrated spectra. How do we bake in the 2 or 3D effects? And then we also have to worry about the fact that this is all happening against the backdrop of a star for transiting planets. And so if some of you have played around with this, and as you'll play around later today, there are different ways of phrasing these things. So sometimes if you're like super flexible and you allow your temperature profile and chemistry to do whatever it wants, those are called free retrievals. If you impose some sort of chemical equilibrium, sometimes those are called chemically consistent retrievals. You can blame Laura Kreidberg for these goofy naming schemes. Yeah, that was you. Not me, it was you. And then if you build in more consistency, sometimes these are called, you can build in like the physics of radiative convective equilibrium, or you can use full 3-dimensional GCMs and produce grids and then Bayesian interpolate over those grids. Sometimes those are called retrievals. That's my fault, but Natasha Batala and Sarah Moran are also complicit in this, so it's not 100% my fault for that naming scheme. So if you hear these terms, that's what they're referring to. So here's a nice figure from Shi Zhang's 1,000-page review paper in 2020. You guys know what I'm talking about. Just summarizing the different shapes of the temperature profiles across the continuum from the solar system to irradiated exoplanets and brown dwarfs in between. So how do we parameterize temperature profiles? So one way of doing it is you actually you discretize your radiative transfer grid, like n layers or whatever, and you can try and fit for each temperature along each layer, but then you'll get a bunch of wiggles and you'll overfit your spectrum. So you can do fancy things like apply smoothing, something that's called Tikhonov regularization, where you can say that each layer is correlated with another, so they can't change too much. Or you can parameterize it. These are 2 common parameterizations that a lot of these retrieval codes that you'll play with use that make different assumptions regarding the physics of the atmosphere. We should stop using this one because it goes isothermal, and that can cause some problems. I'm sorry, I used that once. Chemistry and the abundances, as we saw from Julie, the vertical mixing ratio profiles for different gases can vary widely with altitude. So how do we account for that? Do we assume constant with altitude? Do we have to come up with some kind of prescription to describe the shape of how these behave with decreasing pressure? How do we do that? So there's choices that can be made there. There's also such a weird way of saying this, but 3D effects. So how does the 3D-ness, the 3D geometry of a planet affect what we're going to see? So if you observe like a hot day side and a cold night side, say during like 1st or 3rd quarter phase of a planet during a phase curve, if you use a 1D model, how are you going to be biased if you're trying to fit a two hemisphere thing with a 1D model? You might end up inadvertently introducing biases in your fits. Same thing along the limbs. You can consider things like non-uniform cloud coverage, and if you do or don't, you can get different answers depending on what you assume, right? You see these. This is an example of a marginalized posterior for water. How does this water abundance shift around as you change these multi-dimensional effects? In the interest of time, we'll skip through. So the transit light source effect we heard about a little bit, but if your transiting planet is transiting star spots, you can induce artificial features in your transmission spectrum. And if you were to fit that spectrum without accounting for that, you could get significant biases in things like your metallicity and C to O. But if you try and correct for that, you could maybe correct your biases, but how well we can correct for that is still being worked on. Clouds, as we talked about, can be a nuisance, but also we're trying to learn about them. Not including clouds is a no-no, just don't do that. But there's like a huge gradient in cloud assumptions you can make from anything from full microphysics to simple like phenomenological things like, oh, it's a gray opacity. As long as you include some kind of cloud, you're doing okay. You won't be like totally like off the rocker, but you should explore the gradient of cloud assumptions. And so here's a nice example illustrating how the degree of self-consistency, that gradient from free retrieval to other things can make a difference. And so in the limit of sparse data, you can get different answers for what the composition of the atmosphere is if you neglect certain physics. And so you can sort of see how you can go from having a really high metallicity and high C/O to something more like solar composition if you make these different assumptions about the self-consistency. And here's a nice recent example from a beautiful spectrum from the JWST early release science program, comparing this gradient of self-consistency amongst these different retrieval models, showing that when you do have good data, you do get the same answer for the metallicity, C/O, and this temperature parameter. So if you do use these different assumptions, you can actually get robust inferences. Okay, I'll wrap it up. But I blame Gongwei for this. Yeah, blame the observer, blame the modeler. The data, sometimes if you add more data, you can get a worse fit and you can get constraints that may or may not be consistent with your data. If you get more data, you can change your abundances. That doesn't mean anybody's wrong or right. It just means that you have to be mindful of your data. Different reductions can lead to vastly different differences in what your inferences might be. We're also struggling with this issue with JWST data, depending on whether or not you futz with limb darkening in a different way or account for offsets between different instrument modes. You can throw your C/O ratios and metallicities in different directions. So I think having modelers and retrieval lists talk to the data people more, and that feedback is very important because both, we're still all trying to learn how all of this works. Let's skip through some of this. There are ways we can fix this. There are cool things like this leap one out cross-validation. I encourage you to check out Luis Wellbank's paper. There's lots of applications that I'll have to skip through. High-res stuff, Matteo talked about, brown dwarf things. We can do full things. There are more retrieval codes than there are JWST data sets, so have fun. And here's some Q summary, and then Q pictures while you ask questions. Dexter.
So there's one online question asking your views on using the quenching approximation. Sorry, let me start again. Asking your views on using the quenching approximation in the retrieval model.
Yeah, there's different ways. That's a good question. So the idea, if you are doing a chemically consistent model, you calculate, you can use many off-the-shelf codes that calculate the thermal equilibrium abundance mixing ratio profiles as a function of altitude or pressure. And one way of baking in disequilibrium chemistry from vertical mixing is to just sort of pick up pressure for certain gases like CO and methane that we heard about from Mark earlier today, and say that the effective vertical mixing is going to make those constant with altitude. So you can bake that in with what are called a quench pressure parameter, or you can actually use parameterized schemes that take into account the reaction time scales compared to the vertical mixing time scale, and you can retrieve those directly. So there are ways of baking in quenching into these retrievals. Yeah.
Hi, Mike. There's so many different retrieval approaches these days, and my question is about which ones of them are the most computationally efficient. How, we're burning up a lot of CO2 every time we do these retrievals. So what direction would you recommend taking to minimize the computation cost?
Yeah, no, that's a good, tricky question. I don't want to say you don't want to use certain kinds of retrievals, because I think it's the gradient. It's on the gradient of the assumptions in that grid that I showed. I think we need to do all of them. To actually, that's where the learning happens, is this thing gave me this thing gave me this. So it's on that gradient. In terms of computational efficiency, there are ways that people are trying to speed things up. I have seen some really cool machine learning posters that are trying to speed up the actual nested sampling. So you can use orders of magnitude likelihood evaluation. So I think that's one way to go. So I think we should keep an eye on some of these approximate Bayesian computational methods. I think trying to speed up forward models using, I guess they're called graphics processing units, GPUs, I think a single GPU can replace hundreds of processors, so that would use less energy, but it's trickier to code. So I think a combination of using some of these approximate Bayesian methods, like within the machine learning realm, and then using the hardware, the more efficient hardware, like graphics cards, I think is one way of speeding this up. But I wouldn't want to replace a specific parameterization because I think we need them all.
Thanks.
Yeah.